A little learning is a dangerous thing. A little learning may lead us to believe that we understand things way beyond our comprehension. Great learning is even more dangerous. Great learning opens the door to possibilities and choices, and with choices comes responsibility. Not always a character trait of the human race. No amount of learning is as dangerous and as destructive as ignorance. Certainly, information can be used for good or for evil, but so can ignorance, and ignorance leaves us blind. We are here to listen to the 2025 Nobel lectures, 9 laureates of great learning, 9 dangerous men. It sounds like the title of a Western movie, doesn't it? I look forward to seeing them all riding off into the sunset to the music of the great master Ennio Morricone. Like the heroes of classical westerns, you are indeed armed and dangerous. Armed not with 6 shooters, but with great learning, ready to do battle with the ultimate dangers facing humanity. Disinformation, alternative truths, and chaos. Darkness is strong and will prevail in the absence of light, and while it takes only a single candle to light up the darkest room, a lone candle may easily go out. This is why science is important, but teaching is paramount. Working in research is to learn. Communicating research is to teach. Research without teaching is hiding your light under a bushel. Light should be shared. Gathering and multiplying light leads to enlightenment, and enlightenment, as opposed to mere light, is robust. When Alfred Nobel planned for the conferment of the prizes that bear his name, the Nobel lectures were an integral part of them. In these times of war and climate crisis, when truth itself is under attack, we have more cause than ever to feel gratitude towards Alfred Nobel for his vision to celebrate knowledge, light, and enlightenment. Perfectly aligned with the greatest benefit to mankind, this year's prizes are indeed eminently useful. The prizes in physics and economic sciences celebrate how that which is useful and small can be grown large. The prize in chemistry goes one step further to reveal that there are uses of that which isn't even there. To our laureates in physics, chemistry, and economic sciences, I extend my heartfelt gratitude that you have braved the inconveniences of travel to come to this Ultima Thule at the very edge of the world, to bring light at a time when that is in short supply. Thank you for your willingness to teach. I also want to thank all of you here who have come to listen, in this hall and online, for your willingness to participate in Alfred Nobel's dream about enlightenment. Thank you for your willingness to learn. In the darkness of our Nordic winter, bring it on. Let there be light. Fiat lux. I now invite Olle Eriksson, chair of the Nobel Committee for Physics, to introduce this year's laureates in physics.
Good morning, ladies and gentlemen. You are all accustomed to, in your everyday life, what you see on the screen behind me. On your left, you see a boy throwing a ball onto a wall and it bounces back. And you know in your everyday experience that the picture to the right just doesn't happen, not in the world of classical physics. The ball never ever goes through a forbidden region. In the microcosmos, that of atoms and electrons, this is everyday life experience, and there's no problem with this at all. Alpha decay from the atomic nucleus is one such example. In the early 1980s, late 70s, researchers started to think about if it is possible to also see the quantum mechanical tunneling that is so well known from the microcosmos, if that was also possible in the macrocosmos for macroscopic objects. And it was identified that the most suitable object to investigate such an effect in was that of electrons in a conductor forming a superconducting state. So in the top graph, you see electrons in a normal state in a normal conductor, copper wire, as an example. In the middle panel, you see the superconducting state where electrons pair up and they're holding hands. Those little spherical objects have now paired up into what is known as a Cooper pair. And at very low temperatures, they form a superconducting ground state of Bose-Einstein condensate that has no distinguishability between Cooper pairs. They are all in one big macroscopic object. So this was then investigated to investigate and see if the laws and the discoveries and the phenomena of quantum physics and quantum mechanics could also be seen in macroscopic objects. And a macroscopic object of this kind can be trapped into a potential well, and that's the figure you see on the right. You have the energy of the well on the y-axis, and you have the position on the x-axis. You can imagine this would be you hiking around in the Swedish mountains, and you're in a valley, and you want to come out of this valley, and you cannot tunnel through it. You have to hike above the peak. But in the world of superconducting macroscopic phenomena, this was not quite the case, and the tunneling phenomenon was discovered and described by this year's laureates. And the smoking gun experiment that proved this, that proved the tunneling phenomenon, that is what you see on the left-hand side here. You see the escape rate of this object on the y-axis, and you see its position. That would be your position if you're hiking around in the Swedish mountains on the x-axis. And if the classical world would prevail and describe the rate with which this object would climb out of this well, it would follow the straight line that you see on the left plot. But at low enough temperatures, quantum effects start to play a role, and the curves deviate from the straight line, and this is the smoking gun experiment that demonstrated quantum phenomena of a macroscopic object. You will hear more about this in a second. But first, let me read to you the motivation to this year's Nobel laureates. To John Clarke, University of California, USA, Berkeley. Michel Devray, Yale University, University of California, USA, and Google Quantum AI, and John Martinez, University of California, and QuoLab, USA, for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electrical circuit. So please join me now in welcoming the first speaker of our trio of speakers to the stage to give his presentation.
from slugs to macroscopic quantum phenomena. I would like to talk about this subject in two separate episodes. The first is my work at the Cambridge University, where this was really the ultimate route why I ended up at UC Berkeley. So I will begin with an overview of the work I did many, many years ago at Berkeley. And I will begin with talking about my work at Cambridge University, and then I will move on to talk about my research at UC Berkeley, which talks about three topics: macroscopic variable, energy level quantization, and macroscopic quantum tunneling. So let me start out by talking about my research at Cambridge. I was a graduate student at the Royal Society Modern Laboratory on Free School Lane in Cambridge, and there's a more recent photograph of me. My thesis advisor was Brian Pippard as of the 1st of October 1964, and he set me a rather tough project. He wanted me to be able to measure voltages as small as 10 to the minus 12 or 10 to the minus 13 volts at a time when the state of the art was 10 to the minus 9 volts. Well, I pondered this for a while, and I thought that's going to be a difficult experiment. But a little bit later, Brian Josephson gave a colloquium explaining Josephson tunneling. And this really changed my world, and to be honest, the world of many other people. But he spent quite a lot of time talking about various topics, and one of the ones he talked about was flux quantization. And the basic idea there is that if you have a superconducting ring in which there is superconducting magnetic flux, then the flux is quantized in units of the flux quantum, phi 0, which is equal to Planck's constant over 2e. Of course, he talked about Josephson tunneling, and the basic idea there is that you first of all deposit a thin film of superconductor on an insulating substrate. You then oxidize it, and then you deposit a second film. And that's the basic principle of the Josephson junction. But he went into this in considerably more detail. And on the top left-hand side here, we see an insulating barrier, which is, an insulating barrier which separates two superconductors, and the Cooper pairs, which are what makes superconductors superconducting, are able to tunnel through this barrier. And on the right-hand side, you see the plot from the very first observation experimentally of Josephson tunneling by Anderson Rowell at Bell Labs. And what you see on the vertical axis is the current versus the voltage on the horizontal axis. And at very low currents, no voltage appears, but as you increase the current sufficiently, then you get a transition to the voltage state. And this depends actually on the magnetic field that one is applying. Well, Brian Josephson worked out the two very short equations that explain all this, and they're written here. The first is the current I through the junction, and that's equal to I0 sine delta, where I0 is the maximum supercurrent, or the critical current, and delta is the phase difference across the barrier. In the voltage state, the delta by dt can be written as 2 pi times the voltage divided by the flux quantum. And he did this remarkably in his very first year as a graduate student at Cambridge, and he won the Nobel Prize in 1993. Another very important development that happened just 1 year later, in 1964, was by Jakovic, Lamb, Silver, and Mersereau. And they came up with the idea of the SQUID, the superconducting quantum interference device. And the basic idea is that you have a superconducting ring interrupted by two Josephson junctions. And remarkably, if you start to change the magnetic flux in the loop, then the critical current oscillates as a function of that flux, and the period is phi-0, the flux quantum once again. So the SQUID unites the two ideas of Josephson tunneling and flux quantization. And this is on the right, a figure of the device that they made. And at the bottom, you see there's a superconducting film. And then on top of that, there's a rather thick layer of insulator. And then at each end of that is a Josephson junction. And the plots here are of the Josephson current versus the magnetic field. And if you look here, you see that as you change the magnetic field, there is these oscillations in the critical current. Well, the very next day, my thesis advisor, Brian Pippard, came into my office and he said, "John, how would you like a voltmeter with a resolution of 2 × 10⁻15 volts in 1 second?" And I thought, that would be amazing. But then he explained how you would do this. And here is what he drew on the blackboard. And on the right-hand side, you see a SQUID. And then the inductance of the loop is L, and it's coupled to another inductance with the same inductance L in series with a resistor, so that if you apply a voltage across this input circuit, then you couple flux into the SQUID. And just for simplicity, he said, let's make L equal to M. And basically, that's a digital voltmeter. And the voltage resolution is given by V input, which is equal to I phi-0 times R, and that's the amount of current you have to apply to get one flux quantum in the loop. And if you choose a time constant of 1 second, then you find that the actual resolution is 2 × 10⁻15 volts. And that was quite remarkable at the time. It would represent a 6 order of magnitude improvement in the state of the art. However, there was a problem. The Mon laboratory did not possess the equipment to deposit thin films. And so I couldn't make a device that replicated the kind of device that had been made in the US at the time. And I spent several weeks trying to fabricate a Josephson junction from pieces of niobium foil and niobium wire, sometimes soldered together with lead tin solder, and none of my attempts was successful. Fortunately, my problem was solved one day during our daily tea break, when I was expressing my frustration at not being able to make a Josephson junction. And Paul Raitt, who I remember very well still, a fellow research student, pointed out that niobium has a surface oxide layer, and lead tin solder is a superconducting wire. Why don't you put a blob of solder on a piece of niobium wire? And he was suggesting a device that looks like what's on the left-hand side here. And you can see that there is a niobium wire, and I've put a blob of solder on it, as you can see here. And then there are 2 leads so that we can measure the current voltage characteristics. And before dinner, and then I put the device in my cryostat with some liquid helium, and before dinner, that's what we saw. So once again, we have current on the vertical axis and voltage on the horizontal axis. And what you see is that at low currents, there is no voltage, and then when you increase the voltage sufficiently, then you have a voltage developed. So that was, for me, the beginning of how to make a Josephson junction. The day after, I put this device on my desk, and when Brian Pippard came in the morning, he said, "It looks as though a slug crawled through the window last night and expired on your desk." And so here's a photograph of a slug. So anyway, that decided the name of this device. And so the SLUG was the superconducting low inductance undulatory galvanometer. And so if you now look at this figure here, you find that the SLUG has an extraordinary property, that when you change the current flowing along the niobium wire, the voltage across the SLUG oscillates as a function of this bias current. So quite remarkably, the SLUG behaves as though it were a squid. And this enabled me to make an analog voltmeter with a voltage noise of 10 to the minus 14 volts per root hertz. And so this was still in my first few months of being a graduate student. So I spent a great deal of time after that trying to improve the SLUG, but also doing a variety of experiments that could only be done if you had a sensitivity of this kind. Well, after years went by, I started to ponder about what I should be doing next. And a little while before I graduated, Paul Richards, who at the time was a faculty member of the physics department at UC Berkeley, came to visit my lab. And he was curious to see what I was doing, and also I would like to hear what he was doing for his research. And I really enjoyed meeting him. So, as I said, I was pondering what to do next. It occurred to me that as a postdoctoral scholar, it would be a very interesting trip to the US to go to UC Berkeley, where Paul was a graduate student, was a faculty member. He was a wonderful mentor for me, and he and his family became my close friends. Very sadly, he's no longer with us. So on January the 6th, 1968, I moved to the physics department at the University of California as a postdoc for a year. And I worked away at my SLUGs again and various applications that you could do with them. And they then invited me to become a faculty member and also at the same time a senior scientist at Lawrence Berkeley National Laboratory. And then I started my research group. I, at some point, took on a variety of graduate students and postdocs. And in 1980, John Martinez, who had just received his bachelor's degree at Berkeley, joined my group as a graduate student. And in 1982, Michel Devereux, who had just received his PhD in France from the University of Orsay, joined my group as a postdoctoral scholar. We had to figure out what we'd like to work on. And at the time, there was a very interesting paper and discussion by Tony Leggett, Do Macroscopic Variables Obey Quantum Mechanics? We decided to investigate his intriguing question using a current-biased Josephson junction. And the macroscopic variable is the phase difference delta between the superconducting order parameters on either side of the barrier. So we realized that we had to cool our device to very low temperatures, and so we built a dilution refrigerator and the bottom end is shown here. And this enabled us to get down to temperatures of, say, 18 millikelvin. We also invested a great deal of time to minimize the level of electrical and magnetic noise in the device. And the superconducting device is at the bottom here. So, after our first year or two of work, we published our first paper, our physical review letters, Energy Level Quantization in the Zero Voltage State of a Current Biased Josephson Junction. And let me basically give a brief overview of what that's about. And in this part of the talk, I won't go into any details about what's actually how we work the calculations out. But on the left, we see a cubic potential U versus the phase difference delta, in which there are 3 energy levels. And on the right-hand side, we see the circuit diagram. Here's the junction, shunted by a resistance and a capacitance. You can apply microwaves, and you can apply a bias current, and you can measure the voltage. And the plasma frequency of a device like this is given by this equation, which I won't explain, where phi 0 is the flux quantum. And we can control the energy levels by adjusting the bias current I. Well, the first thing that we discovered was that if we apply microwaves, then the escape rate can be enhanced. And the escape rate gamma out of the well in the presence of microwaves of power P is resonantly enhanced over that in the absence of microwaves when the microwave frequency corresponds to the spacing between 2 energy levels. And the change in the escape rate is given by gamma P minus gamma 0 over gamma 0. So we start to investigate various properties, and here I'm showing the escape rate versus the bias current. And this is a plot of our parameter gamma P minus gamma 0 over gamma 0 in the presence of 2.2 gigahertz microwaves. And what we see is, if we look at the result of doing this, is that we can observe 3 peaks, and these correspond to transitions shown above. For example, the right-hand one is the 0 to 1 transition, which is the right-hand peak. Here is the 1 to 2, and here is the 2 to 3. And so these peaks get sort of weaker as you go to these higher transition levels. And then the lower plot is the calculated energy level spacings of the transition from the n state to the n plus 1 state versus the bias current. And here, for example, is the 0 to 1 transition. Here's the 1 to 2, 2 to 3. And the dotted lines here indicate the values, indicate the errors in the critical current and the capacitance. And the arrows here indicate which transition we're looking at. Well, now let's look at the frequency, microwave frequency dependence. And in the top curve, that is A, we're looking at gamma P minus gamma 0 over gamma 0 versus the bias current in the presence of 4 different microwave frequencies, which are labeled here. And in B, we're looking at the calculated energy level spacings versus the current bias. So these are the different spacing levels, and the arrows indicate the values of bias current at which resonances are predicted. The dashed line out here is the plasma frequency. The shift in the positions of resonances as the microwave frequency is changed is in excellent agreement with the predictions. Well, another thing that interested us is the evolution from quantum to classical behavior. And at the lowest temperature, that's the bottom plot here, we see a single resonance. As we increase the temperature, which is measured here in terms of k-Boltzmann T over h bar omega, the frequency, what we see is that an additional shoulder begins to appear, and at the highest frequency, A, the response is a continuum, and that implies that we are looking at classical behavior. So to summarize this first paper, we observed microwave-induced resonances, resonant enhancement of the rate at which current-biased Josephson tunnel junctions escape from the zero voltage state. The positions of these resonances are in excellent agreement with the predictions of a model in which the energy levels are quantized with no fitting parameters. These results provide very strong evidence for the quantum behavior of the macroscopic variable delta. Well, now let's move on to our second paper, which was published just 3 weeks later. Measurements of macroscopic quantum tunneling out of the zero voltage state of a current-biased Josephson junction. So once again, I will go through this paper and mostly focus on showing the figures, and some of the details like this I won't take the trouble or won't have the time to go through. But just to summarize a couple of things, in the thermal regime, meaning k-Boltzmann T much greater than h bar omega plasma, the particle escapes from the well via what's called thermal activation. So it's a thermal process, and the equations are written here. On the other hand, in the quantum regime, k-Boltzmann T much less than h bar omega plasma, the escape is predicted to occur via macroscopic quantum tunneling at a rate that, again, we calculated. And the only number I'll mention here is that the crossover temperature at which the energy rate changes from thermal temperature-dependent to quantum temperature-independent is predicted to be h bar omega plasma over 2 pi k-Boltzmann in the limit q much greater than 1. And Q is the damping factor, omega plasma times RC. Well, it turns out that a very useful and important characterization of all this is the escape temperature T sub ESC. And to express the experimental measurements of the escape rate in a way that is independent as possible of the parameters of the junction, we introduce the escape temperature T escape. And that is defined through the result I've shown here. In the thermal regime, we have one prediction, which involves the parameters here. And in the quantum regime, at T equal to 0, the prediction is again given by this complicated equation. And the crossover temperature at which the escape rate changes from thermal, meaning temperature dependent, to quantum, temperature independent, is predicted to be h bar omega plasma over 2 pi k-Boltzmann in the limit q much greater than 1. Well, here's another plot, which you also saw a little while ago. And this is T escape versus temperature for 2 values of critical current. And there is the so-called quantum junction, which has a relatively high critical current. So the quantum junction is one with a relatively high critical current, and the classical junction has a much lower critical current. And the two arrows here, for the solid arrow represents the predicted crossover temperature for the higher critical current, and the open arrow here is for the lower critical current. The predicted value of the escape rate, which is plotted here versus temperature, is indicated here on the left with this little symbol here. And what you see is it lines up really rather accurately with the bottom end of the quantum plot. And the lower temperature value of the T escape are in good agreement with the T equal to 0 predictions shown here. So this was a very important result. And what we've finally wanted to end up with is the dependence of the escape temperature on the bias current I. And I show the results here at two different temperatures. In the upper figure A, at 151 millikelvin, we're in the classical regime, and T escape decreases with the increasing bias current. The lower plot shows the result at much lower temperatures. And what you see here is that the T escape increases as you increase the bias current. And within the experimental uncertainties, the data are in good agreement with the theory. The very different dependence of T escape on the bias current in A and B demonstrates that the escape mechanisms are different in the classical and quantum regimes. So, in summary, we measured the escape rate of a current-biased Josephson junction from the zero-voltage state for two values of critical current. For the lower critical current, T escape followed the classical prediction to within experimental error. For the higher critical current, T escape was equal to T at higher temperatures that began to flatten off at temperatures below 50 millikelvin, becoming temperature independent 25 millikelvin. Within the experimental uncertainties, the low temperature value of T escape was in excellent agreement with the zero temperature theoretical prediction for macroscopic quantum tunneling, with all relevant parameters measured in situ in the classical limit. The combined results, the combination of the result from these two publications provided very strong evidence for the existence of energy quantization and macroscopic tunneling in an electrical circuit. For this work, as you know, we were very privileged to receive the Nobel Prize, and the citation was for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electrical circuit. And in conclusion, I would just like to note that there were various other groups also working on macroscopic quantum tunneling who also made very important contributions. So thank you very much for listening.